Yeah, thank you very much. So we're going to start just now, and today we're going to go to the load flow straight away and discuss the various theoretical parts and hopefully progress as expected. So last time I talked about these few things that are related to the load flow study in terms of the operational features and looking at the electrical performance of our power systems. Three main areas were load flow problem, optimal scheduling, and the systems control problem that I talked about. Now, when we come to this load flow, actually, in terms of the power system operation, when we talk about the load flow, we look at the steady state solution, meaning when the power is being generated and transmitted and being consumed, the power system as a whole maintains a steady state. That's what we want, and that's what we are actually focusing on to study in this chapter. There are other studies as well, like transient study, subtransient study, fault analysis, many other different types of studies that we do, literally studies in power system. But in this one, it's a steady state solution. And when we do so, what we do, we model the power system under consideration as an electric network, and we try to solve for the steady state power and the voltages at the buses that power system has. So there will be a lot of buses involved in a power system. In modern generation, we have a lot of buses, thousands of buses, and we need to know the power flow and we need to know the voltages of those various buses. Now, the main reason why we do the power flow study is to ensure that the power system is operating at a steady state, and not only that, uh, we also need to know the parameters specifically, especially the powers, active power and reactive power, and the voltages and their magnitudes and the phase angles. So we need to know all of them, but when we do so, we get those information like the ones that you see on the screen, the magnitude and phase angle of voltages of the load bus. It's not that we get all these four parameters: active power, reactive power, voltage magnitude, and voltage phase angle. We get all these things, or we look at all these things for each of those buses or everywhere. It's not like that. We get specific information from specific buses or specific place, a part of the power system. For example, if it's a load bus, we get the magnitude and phase angle of the voltage. If it's a generator bus, then we get the reactive power and the voltage phase angle. We don't get the others. Similarly, if we look at the transmission line, we get the real and reactive power. There are different types of buses that I just mentioned, two of them, load bus and generator bus, on the bullet point A and B. But there are other types of buses as well. I'll discuss them later on. So when we come across different types of buses, so according to the bus, we will have something known and something unknown, and we will have to solve for all those are unknown. So the information that we get from the power flow studies, we use them for planning purposes. And the planning also falls somehow in the continuous monitoring. So there are main two categories that we use this information from load flow study is for continuous monitoring of the current state of the power system, meaning each and every second we're looking at what is happening in the power system and we make sure that it's steady. We cannot have an unsteady or unstable power system. So the next one is that analyzing the effectiveness of alternative plants, because we know now how much power is being generated, how much is being consumed, by which type of consumer. So from that we can plan for future, because if we don't plan for future, we will not know what to do in next week or next month or next season, or after 2 years, after 5 years, or after 10 or 20 years. We don't know if we don't have a proper plan. So we use all the information from the load flow studies to plan for future. And when we do so, mainly we look at various aspects. First of all is the addition of new generators, meaning do we need to add new generators, how many of them, what should be their capacity, and what type of generators should be included. Is it going to be coal fired power station, or it's nuclear or wind turbine or solar photovoltaic power station? We need to plan all of this, not only just one thing that we need to add some new generators. A lot of story behind, actually a lot of planning behind that, and it goes to everywhere. It's, for example, if it's a coal fire power plant that we are planning for, then we need to know even where the location will be, like the number, bullet point B, which is the sites for the new generators, and then where the water will come from, where the coal is going to come from, where the ashes will be dumped, and everything. So we look at those aspects. Site for new generation, if we putting a new generator in terms of wind power generation, where the wind is blowing all the time almost, and if we are putting a hydroelectric power plant where we can build a big dam where we can store huge amount of water at a very high level, so that the potential energy is high. So we look at those things and finally decide in the planning activities. Next thing is the meeting the increased load demand. As we know that we are always trying to connect our consumers to this power system every day, so the load is increasing. So how we are going to meet that demand? Not just by connecting the new generators, we need to know in which areas the loads are increasing, which areas are still the same, not much increase. If we consider there are various unique type of thing happens in every country. For example, in some cases you might find that there is an area in some place which is only having industrial uh, uh, premises, where there is no domestic houses, or people not living there, things like that. So after some year, what might happen, those industries will become old and they will start shutting down. The power demand might decrease in those areas. So when we trying to meet the demand, we also need to know in which areas it is happening. And according to that, we go to the next step. So when we know where the load is increasing very fast, or increasing moderately, or at a very low rate, where the load actually is decreasing, so we locate where our new transmission lines need to be installed. So it's a very intensive kind of planning activity. It involves a lot of money, a lot of proper planning, and so on, so that we can meet the increased power demand. Now, the next paragraph that you see on the screen uh, is something very important that we need to know. The reason is that so far we have been solving power system problems in our various modules, where there are generators and we are given some impedances, then we calculate current, we calculate power and losses and things like that. But when you come to load flow study, we cannot do that kind of calculation and analysis, because the loads are not impedances anymore. In our second year, third year practices, we used to give load impedance, RL or RC or RLC, that kind of thing. But in load flow study, loads are power. They are consuming active and reactive power. a combination of active and reactive power. Similarly, the generators are not voltage sources. When we did those kind of numerical tutorials in our previous modules, we were given a source which is actually voltage source. We knew, or we were given the voltage of that source, so we use that voltage and then use the RL to find out the impedance, then we can find the current, power, and so on. But in this case, generators are the sources and they behave like power source because they are supplying that active and reactive power which is going to be consumed by the loads which are also power. So in this case, we are dealing with power. Both the generator and the load, they are having complex power, P and Q, active and reactive. So that's why we cannot do direct calculation and analysis in load flow study, because they are not voltage source. The power sources are not voltage sources. They are power sources. They supply power, active power and reactive power. And loads are not impedances. They are complex powers. They either consume active power or reactive power, and a combination sometime. Now we coming to some sort of history. In olden days, very olden days, like not like 20 years or so, if even before that, people were doing load flow study using something called AC calculating board. And AC calculating board is nothing but it's a smaller version of actual network, and it has all those voltage sources. They did not have power source, they were using voltage source, and then they used phase shifter to generate active power, reactive power, or consume active or reactive power, and so on. Sorry, reactive power for phase shifter. And then the line impedances will be there, R and L. Admittances, if you want to take the reciprocal of impedance, and the loads were there in terms of the R and L. Now, what was happening with these things, that they tried to make it such that AC calculating board will show all the components of the power system under consideration, but it in a smaller version. And to make it even smaller, they were not operating that AC calculating board at the rated frequency, which is either 50 Hz or 60 Hz, but they were choosing it to be very high as compared to the standard frequency, like for example 400 Hz, which is like 8 times the 50 Hz frequency. The advantage of that is it reduces the sizes of the inductors and capacitors that are used in that AC calculating board to represent the power system. So that's what they're doing. But what was happening, in AC calculating boards, they were applying some known load with known power factor, and the generators loads were observed. So they take some note and then they do some calculation for power flow study. They determine the active and reactive power that is to be supplied by a particular bus, and then what are the powers consumed by other buses, what are the voltage magnitude and phase angles at other buses. That's what they were doing. But as the power system started growing bigger and bigger, it becomes too difficult to represent those big power systems into a small calculating board. Although we might use high frequency and getting the sizes of inductor and capacitor reduced, but it's very difficult, it's complicated, and it's time consuming, very, very time consuming as well. And in most of the cases, what we need to do, we need to repeat the same procedure to get accurate result, or the result that we expect. And to do so, it will take very long time. But fortunately, we have very fast digital computers these days, and we also have some softwares that are being used by the scientists and researchers and the power system engineers as well in real power utilities to do the power system load flow studies. And it's very easy to do such thing, and it's also less time consuming. It's not that tedious. If you want to repeat, it can repeat as many times as you want, or the algorithm itself can be programmed such that it stops the repetition or iteration once it converges to a value where no better value can be achieved or found after the completion of that algorithm. So these days we use computer software, like all those software that you are going to use in your electrical engineering. MATLAB can do the power flow study, PSCAN can do, RSCAT can do that power flow study as well. But together with that, we use some methods like I gave you in your tutorial, that Gauss-Seidel, then Newton-Raphson method, that first decoupled method. We use those algorithms where we write codes, and those codes are nothing but algorithm, and they give us the best solution in terms of those four parameters that you must remember: active power, reactive power, voltage magnitude, and voltage phase angles. And out of those three methods that I gave you in tutorial, Gauss-Seidel, Newton-Raphson, and first decoupled method, we are going to use the Gauss-Seidel method for some tutorial, because that's easy as compared to the other two methods for doing hand calculation, and it needs some iterations, sometimes 6, 7 or 10 iterations, but we cannot do all those iterations. It will take time, so we try to understand the philosophy of that algorithm, and maybe we'll stop after 3 iterations and so on, and we will be able to see what is happening as we go from iteration number 1 to iteration number 2 and iteration number 3. So it must show us that the value of those powers, active and reactive, and voltage magnitude and phase angle, are converging to a very good value that are acceptable. So we use computer algorithms these days. So now I'm coming to what is happening. Hey, this is jumping too much. Okay, because of this figure, sorry about that. I should have made it large initially. So now I'm coming to some examples of real power system, but in a smaller version. Because if we understand the smaller version of a power system, we will be able to understand the bigger version of it. It's easy to follow. It's just addition of buses, nothing else. And when we add buses, definitely we add something in terms of electrical equipment. It might be a generator, it might be a transmission line, or it might be some load, direct load. So when we talk about power systems now and load flow studies, what we come across, the buzzword or keyword here is the bus. So sometimes you ask what is a bus. What I did here, I put some pictures of buses here just to show you how they look like. This is a picture showing 3-phase system, and these are the buses. This is the copper rectangular cross-sectional area buses are there, and they are very thick. In some cases they are thin like this one. We get thicker and wider as well, and these are the cities connected to each of those buses. So they look like, actually, a bus. If you want to define it, or you want to know what is a bus is nothing but a collector and supplier at the same time of electrical current or power. So it takes power or current and then it supplies. So the word bus actually is very unique, and when you use it together with bus bar, these are called bus bar because they look like bars. So we call them bus bar in electrical engineering. But the word bus is very general, and not those bus that we used to take a ride on to go from one place to the other. But if you go to mechanical engineering, they handle with flow of many liquids, gas, pipelines are there. So from those pipelines, they also form a bus. Like, for example, in our houses, what happens? We get one pipeline coming into our house from the municipality, and then we distribute it to our various rooms, or like kitchen, toilet, garden. So it actually has a bus where we connect that incoming line, and then from that bus we distribute it, meaning it's collecting and supplying. So it's the same thing we do here. We collect the current and then we supply. In substation, for example, if I show you the other one, there are various types is a very heavy one. You can see it carries a lot of current. This dimension will depend on cross section area, will depend on how much current the bus bar is supposed to carry. So that's another picture of bus bar. It normally comes with so this is another ROIB bus bar is for the high voltage, high current, high power applications like 6.6 kV, 11 kV, 33 kV, and so on inside the distribution station or a substation. They look like that. And there is another one, and to make it big, small circuit, but how they are distributing, can you see? Now this is taking power from, these are the incomers, they are connected to three of them ROIB, and these are outgoings, and they are connected via these switches. Like the same thing you do it in mechanical pipeline, that example I was giving. In your kitchen, in your garden, in your toilet, there is a tap, you shut it. So it's the same thing, that switches are there. So when you are taking incoming and outgoing through a bus bar, you must make sure that at the incoming side and outgoing side there are some isolating devices. Those taps are nothing but isolating devices, because if you don't shut them, then water will be always getting drained and you pay for that. Same thing if you want to stop something here in terms of load flow, power consumption, then you use that switch, because that is also very important in terms of protection. When something goes wrong in our electrical and mechanical operation, we immediately shut it down. Like if you found that a pipe is burst where the water was flowing, so what you do, that you shut the incoming valve off. The same thing, if you find that something is wrong in the bus bar or in the outgoing, the switch is not working, so you switch off the incomer circuit breaker. The bus bars are also there in our substation, outdoor substation. This is a photo from outdoor substation. It's not looking like the other examples that I showed you. It's the bus bar outdoor. So it's simply those transmission line conductors, very similar to that. It has stranded conductors, and then we use them as bus bar. And what we do in substation, incoming transmission lines are there, and we connect those incoming transmission lines to the bus bar, and from the bus bar we connect a number of transformers, and at the secondary side of the transformer we also take them to the outgoing bus bar, and from the outgoing bus bars we might have some direct load, we might have some transmission line or sub transmission line going out of that substation. So there are various types of bus bars, or their sizes or dimensions or the shapes, everything differs where we are using them. It's always there, even at our households. And for electricity, we are similar like the example I gave you for water supply. We have one pipeline coming into our house. The same thing happens with our electricity as well. We get only one phase coming in, phase and neutral. Then we distribute it to all our rooms through a bus bar system. So when we talk about that bus, we'll come to different types of bus bar after a few slides, but let's consider that we have a 4 bus or 5 bus system. I'm showing the 5 bus one first, then I'll come to another example with 4 bus system. So what happens with these buses? These are the buses, that thick horizontal black lines that you see. These are the buses, and they are numbered like bus 1, bus 2, bus 3, bus 4, bus 5, and so on. So as this system has 5 buses on it, we call it a 5 bus system. If a system has 3 buses in it, then we call it a 3 bus system. If the bus has 30 buses in it, then we will call it a 30 bus system. That's how I gave you those examples, that it's a 6 bus system, 14 bus system, 30 bus system, meaning it has those number of buses like that number. Now to each of those bus there will be something. For example, in bus 1, what are the things there? First of all, we need to know the voltages of each bus. So bus 1 has voltage V1, bus 2 has voltage V2, bus 3 has voltage V3, bus 4 has voltage V4, and bus 5 as voltage V5. So they are labeled according to the number of the bus. Bus 1 cannot have V2. We cannot make mistake like that. It's simple. Then what we have here is this circle here is representing a generator, and then a generator is supplying complex power S. S is complex power, which is P plus G JQ, P plus JQ, and SG1 meaning complex power of generator 1. In this bus 2, we have another generator which we named as G2. It is also supplying some complex power S. So whatever we getting from it is labeled as SG2. And similarly, if we come to this bus number 3, there is no generator here. What is there? What is written here is SD3. D is for demand, meaning it is a load, so it has only a load connected, but it is getting power from bus 1 through this connector. So there is an interconnection between bus 1 and bus 3. Similarly, if we go to bus 2, not only that this bus 2 has its own generator G2, it also has an interconnection between them, between bus 1 and bus 2. The reason why we do it to increase the reliability of power supply. In case the power is not coming from the generator 1, G1 is shut down, or we're doing some maintenance, or it has some faults, things like that. So we will be still able to supply this SD3 from this generator G2 via this interconnection and this bus 3. So that's why we do those interconnections. Similarly, we can see there is an interconnection between bus 3 and 4, and bus 2 and 4, bus 2 and 5 as well. But there is no interconnection between 1 and 4, 1 and 5 as well. We don't need that. We can make that route by the existing interconnections. So that's how those numbers and the parameters are defined in the first place. Now if we go to consider the model formulation for power flow study, we consider something very simple for a part of a power system or a power system. It might be a complete power system, or it might be a part of a power system, but it does not matter what we do. Initially we need to know how many buses are there, like the previous example was of 5 bus. So it was 5 bus system. So we need to know how many buses are there. If we don't know, when we formulate our theory, we consider that it will have n number of buses in it, and for that n number of bus system, we will need to consider each and everything for each and every bus. Meaning each and everything means all those 4 parameters: active, reactive powers, voltage magnitude, and phase angle. And we start with any bus. We can start with any bus, but in our hand calculation we will start with bus number 1 and so on. We'll see how it goes. Bus number 2, bus number 3, but it depends on what type of bus that we are considering. We cannot possibly start with bus 1 for each and every case. We might have to start with bus 2 or bus 3. So we consider that we have taken one bus of that n bus system, and we consider that bus is labeled as ith bus, and that I will vary from 1 to n. It's not from 0 to n, because we will have bus number 1, bus number 2, bus number 3, bus number 4 until we reach the bus number n. So that's how we represent very we represent the simple form of the ith bus of an n bus system. This is the ith bus, the thick vertical line, and it has some generating sources supplying complex power, and SGI meaning the generation to the ith bus, and the power is complex. And from the bus we will have some transmission lines, and they will have complex power. So SI, complex power of the ith bus, and SDI meaning the complex load demand of the ith bus. So that's how the generic representation of the ith bus. And if we look at the ith bus, how do we represent those powers? Complex power is simple, like I mentioned earlier, is the P plus JQ. So P plus JQ, but we make sure that we use those levelings accordingly. So is GI generation, so is G should be there and I should be there. If we considering the load power, so SDI should be PDI and JQDI. If we are considering the simple power of that ith bus is SI, it will be PI and QI. And again, we can use the same equation for all the buses starting from 1 up until the n. So bus number 1 to bus number n can be represented in mathematical formulation for power, and from that power we can use the algorithms for calculation of other powers and voltage magnitude and phase angles. So this is just another explanation here. Now I'm coming to the relation between bus currents and bus voltages, but before I come to that, I want to know if you have any question of what I mentioned. Do you have any question, anyone? No question? Okay, let me go to this next section then, where we try to understand the relationship between the bus current and bus voltage. Bus current and bus voltage, how they are related. So to understand that, as you can see, we are talking about bus current and bus voltage. So either there should be admittance or impedance, because we know the formula V is equal to IZ. So when we talk about V and I, there should be Z. So if we don't want to use Z, we can use Y, which is the admittance, which is the reciprocal of the impedance. So we start with the admittance, because in power flow studies there are some advantages of using admittance instead of impedance. So when you talk about the admittance, how we find out those admittance, you see how it is written, small yk, there will be capital YK later on. So you must know the difference between small y and capital Y in this case. And when we do the handwriting, sometimes we cannot make it different for small y, lowercase y and uppercase y, then it will be a mess up. So make sure that you write them properly. Small y and capital Y, will need them actually in Gauss-Seidel method when we will do the tutorial. And they cannot be the same, they are different. So we represent YIK, meaning the admittance between the ith bus and kth bus. The admittance Y is admittance ith bus and kth bus. So admittance between ith bus and kth bus. But again, here we have to remember that I cannot be equal to K in this case, meaning the bus is connected to itself. Cannot be the case here. So YIK is represented as the admittance between ith bus and kth bus. YI0, this is 0, this is not O. 0 is represented for ground. So it's the admittance between the ith bus and the ground. And if we have YIK, where YIK actually is 0, this is also 0, meaning there is no interconnection between ith bus and kth bus, like I was showing in previous case, that between bus 1 and 5 there is no interconnection. So if I say y1 5, y1 small y 1 5 will be equal to 0. So that's how we find it. Small y1 2 will have some value, because there is an interconnection between them. So that's how we represent those admittances for the interconnection between two buses, ith bus and kth bus, between a bus and the ground, and if there is no connection between any two buses, and we generalize them as the ith bus and kth bus, and it will come to the example like bus number 1 is I and bus number 5 is K. So we know now yik, meaning y15 is equal to 0, because there is no interconnection between them. That's what we see there. And after that, what we do when we have those admittances, then we apply the Kirchhoff's current law to ith bus. And when we do that, we consider all those admittances and the voltages and write the equation. Current is nothing but admittance time voltage. So we take all those admittances, I0, then I1, I2, I3, I4, I5, until we reach IN. So when we do that, then we get the current of the ith bus. And we can manipulate this equation, write it like this in terms of V1, V2, because they are mixed here. V1, V2 are they are mixed, so we separate them. V1, V2, V3, V4, and Vn is the last voltage, because we have n number of buses, so we will have V1, V2, V3, V4, V5 until we reach Vn. So we separate them, and then finally we can write that equation in a simple manner where we replace those small y's by a capital Y, where we write them like this: yi1 v1, yi2 v2, yi3 v3, yi4 v4. At some point we will reach yii vi, and then finally we will reach yin Vn. So that's the general expression for the current of the ith bus, and we can simplify that one like this. Again, this yik here must be associated with this constraint that it cannot be giving us a condition where I is equal to k, and this formula for calculating yik is I over v, so it's not difficult. So let's come to into more details. I'll come to this one with the matrix, that will help you to understand it easily. So when we do the model formulation, network model formulation, what we try to do first of all, we try to find out the admittance bus matrix. It's a matrix because it has n number of buses. So from n number of buses we will get n number of currents, we will get n number of voltage, and we will get n times n a matrix. So if we have 5 buses, so 5 times 5. If it is a 3 bus system, 3 times 3. So and how the matrix will look like? The matrix will look like this. For the currents is I1, I2, I3 up until IN, V1, V2, V3 up until Vn. But for the admittance matrix, Y11, Y2, Y13, Yn4, Yn5 until we reach 1n. And n can be 100, n can be 10, n can be 3, n can be 5. It depends on how many buses are there in the system. Similarly, next row we go to the y21, 22, and so on until we reach the nth value. So the final value here will be ynn. So we start with y11, we reach at ynn at the end. So that's how the matrix admittance bus matrix will look like. But don't worry, how do we formulate it now? I will come and show the example and you will do it yourself. It's not that difficult. But the interesting thing here is to look at the admittance bus matrix. If we look at this matrix here, if we look at the diagonal, we find that they are having y11, y22, y33, 44, 55, yn. And these are self admittances because they are connected to themselves. 1 is connected to 1, 2 is connected to 2, 3 is connected to 3, 4 is connected to 4, and so on. But actually it's not like 1 is connected to 1, 2 is connected to 2. It's all the admittances that are connected to bus 1. Is the admittances between bus 1 and 2. It's the admittances between bus 1 and bus n. Is the admittances between bus 2 and bus 1. Is the admittances connected to bus 2. Is all the admittances connected to bus number n. But for the others, is between, it's bus number n and bus number 1, bus number n and bus number 2. If we come here, it's the same thing, bus number 2 and bus number n. So diagonal is giving the self admittances, whereas the off diagonal elements, you see 1 2 2 1 1 3, here will be 3 1 4 1 5 1 and so on. They are transfer admittances because they are the interconnections between the two buses, like for example bus 1 and 2, or bus 1 and 3, bus 3 and 5, bus 5 and 1 and so on. So they give us transfer admittance. So when we talk about transfer admittance, we must know that this is the admittance between those two buses. And if we talk about self admittance, meaning it's all the admittances that are connected to that particular bus. Y11 means all the admittances connected to that bus. Y55 means all the admittances connected to bus number 5 only. Now, if we look at the other features of it, we find that it's a symmetric matrix. If we look at here, Y12 and 21, they are actually same. 13 and 31 will be same. 14 and 41 will be same. 15 and 51 will be same. So it's actually a symmetric matrix. And also in this matrix, there will be some cases, some values with 0, because there will be no connection between ith bus and kth bus, and these two are very important as well, because this actually helps us to reduce the calculation, the time of calculation, the memory capacity required. Even if we are doing power flow study using computer softwares or algorithms, we still need some memory in our computer. So this thing reduces the computation and memory space both, because sometimes we'll find that it's easy to see that we don't need to do calculation for all the elements of this matrix at all. Because if I have calculated 1 2, I will know 2 1. If I have calculated 1 3, I will know 3 1 automatically. So it saves. That's why we use admittance for power flow calculation. But if you want to use impedance instead of admittance, it will be the same thing. So we can find out that equation, V is equal to Iz, and we put that V, V1, V2, V3 in a column. Current is also a column, and Z is the matrix that is coming from n bus system. So again, it's Z11, Z12 up until Z1n, and we finally end up having Znn. So it's also n by n matrix. It also has its own properties. So self impedance, it was self admittance for Y bus matrix, and for Z bus matrix it will be self impedance, and it will be the transfer impedance between two buses because it's sitting at the off diagonal locations. And then it will also be an n by n matrix, and this is also symmetric matrix. Again, it helps. Now we use the bus admittance matrix. The reason is it's very easy to prepare the data for power flow. It's simple to do the data preparation. It's easy to formulate the bus matrix. We can do it manually. We can change it when the power system changes, and it's very important. When the power system changes means it just doesn't necessarily mean it just doesn't change, because we have our power system. And how it can change? It can change. For example, we have a power system where we have 4 lines. One of the line is not carrying any current because it's shut down. We are going to have a maintenance. So that power system is now different as compared to if all the lines were in operation. Now in next week we are going to put the new that power line that was under maintenance, bringing back into operation. So line number 5 is now in the system. So we have to modify the admittance bus matrix. To do so, it's easy. You including or excluding, taking into account or removing it from the system. So it's very easy to do. So we'll do some changes like that and see. And the sparsity of the matrix, that reduces the computation time and computer memory as well. That's what I was trying to mention in the previous slide. Now I'm coming with another example with 4 bus system, showing how that matrix for the admittance is formed and how the difference is between the lowercase y and uppercase y, because both of them are admittances. Y means admittance in our electrical engineering. But before I go there, can I take a question? Okay, it's 2 p.m. I did not even look at the watch, so I have to stop it here.